All right, boys and girls, welcome back to the drive-through. We're here with the final Algebra 2 video. Boom. Love it. It's all about vectors. Vectors are really critical in physics. They're becoming more and more useful in general because we know how to manipulate them more. And the thing that you got to know about vectors is they have direction and magnitude. So you should think about a vector like an arrow with an original starting point and an end point. Okay, so the direction is the length of the arrow. The magnitude is the length of the arrow, and the direction is the orientation of the arrow, or which way the arrow is going. So notice some people in the Sim Lab are not vectors. They completely lack direction. But the good news is they'll never hear that joke because they won't get this far. They'll be somewhere else by that point, so not a big deal. So a scalar is just a name for a number. A scalar is a magnitude. So like, you're going to hear those words, and I don't want you to be intimidated by them. It's just a scalar is a number, a vector is a number, and a direction. So let's find the magnitude of this vector. That's how you write a vector. It's kind of like an ordered pair, but you use these triangular brackets. And what that means is that on an axis, this vector will go from 0, 0 to -1, 4. Whoops, sorry, undo that. 0, 0. So this right here, that's the vector, -1, 4. How big is that vector? Well, to find how big it is, you just do the Pythagorean theorem. This is 1, that's 4. So the magnitude of this vector, let's say m squared, magnitude squared, is 1 squared plus 4 squared. So the magnitude squared is 1 plus 16. I'm writing out all my steps. You guys could do this in your head. So the magnitude of this vector is radical 17, or about 4 point something small. Okay? This is really just all about talking the language. That's what this whole video is about. So now let's look at a geometric representation for vector addition, subtraction, and multiplication. Let's say we got A is 1, 3. B is the vector -2, -2. And C is the vector 4, 1. Okay? So what does A plus B mean? Well, one thing I want you to know about vectors that's kind of strange is they do not have a position. They can be anywhere on the map, but that also is kind of convenient. So if we look at A as 1 over 1 up 3, so that's A right there. I wonder if I used a bigger font, if it would make me more accurate with the way I graphed. Let's see. Be nice to find this out like a long time ago. Alright, not bad. So that's A. I don't like it. I don't like it. It's too thick. Let's try this one. So there's A. And B is -2, -2. So there's B. And C is 4, 1. So there's C. Well, what does A plus B mean? Okay, well, A plus B means, I'm going to get rid of C for now. We start at 0, 0 if we want. It doesn't matter. We can start wherever we want, but that's an easy way to explain it. Completely quitting on this sticker font. I hate it. So we start at 0, 0 and we go in the A direction and magnitude. But then from there we take B and we go left 2 and down 2, which means we go right back to there. Well, what's the resultant vector? It's that one. That would be the actual distance that we traveled if we went A and then we also went B. We would end up at that pink vector. So now let's do it. A plus B equals 1, 3 plus -2, -2. And that result, you just add the components, is -1, -1. Well, sweet. That's what the pink one is. Hold on, -1, +1. Even better, because that's what the pink one is. Holy cow. Okay? So that's what it means to add. When you subtract, first of all, you should know that the book might write this like this. 1, 3 plus -2, -2. And that is -1, 1. That's the exact same thing. So what does A minus C? Well, that's easy. A minus C is the same thing as A plus -C. So that's the same thing as addition. So I don't have to explain the geometric representation of that. What does it mean when we take a scalar and we multiply it by a vector? Well, that's just 3A, which is 3 times 1, 3, which is 3, 9. And this kind of looks like the dilation one. So that's 3A. Well, that makes sense. That's literally the 3 times the magnitude in the exact same direction as A. So now we'll do some dot products. The dot product is an operation between two vectors, and you really should consider it like a compatibility test. Okay? It's like if the vectors were dating, they could take this test early in the relationship and decide whether or not they were a good match. And remember that opposites attract. So, if the product is positive, the vectors had the same direction. So let's look at this vector right there, which is 5, 1. And let's take its dot product with the vector, I don't know, how about this one, which appears to be 3, 5. How do you take the dot product? Well, 5, 1 dot 3, 5. That is 5 times 3 plus 1 times 5. Oh, it's a scalar. So it is a operation that you take with two vectors, and when you answer it, you get 15 plus 5, you get 20. Notice that these are headed in the same direction. The angle between the vectors are acute, and the dot product is positive. Okay? So let's look at this pink one, which is 1, 2, 3, 4, 5, 6, 3. And let's look at this one. I meant to go to there. So we got -1, 2, 3, 4, 5, 6, 7, 8. -8, -9. 1, 2, 3, 4, 5. This is -9, 5. Okay? Notice that the measurement between these two angles is obtuse. So you might think, well, they don't have a good compatibility score. Well, you have to be careful about that. What if the pink one indicates someone that loves music and the black one indicates someone that hates music? But they would have a lot to talk about. They could talk to each other about, why do you love music so much? This is why. Why do you hate some music much? And they might be perfect for each other. They could go to concerts by themselves, or go to concerts and talk about their shared experiences. So this actually might be a fairly compatible group. Let's find the dot product. So 6 ViewSonic, 6, 3 dot -9, 5 is, it's 6 times -5, sorry, 6 times -9 plus 3 times 5. So that looks like a matrix multiplication to me. And you get negative 54 plus 15. You get negative 39, and I'm just telling you that this information that I gave you before was right. These two vectors are obtuse. They're headed in completely different directions, and the dot product is negative. So the dot product is just a nice way for you to visualize the relationship between the vectors. But here's the most important one. Let's take the one that's maybe like 3, 4. Let's take this vector. And then let's use this one that's 4, negative 3. I'm ready to just get rid of the ViewSonic, but it's too late. We're done. It's no big deal. 4, negative 3. And let's look at the dot product between those vectors. You get 3 times 4 is 12. Plus 4 times negative 3 is negative 12. Aha. You get 0, and check out that angle. That is a right angle. Those are the vectors that should not be dating each other. They literally have nothing in common. One likes sports, the other one hates music. So they won't have anything to talk about. Is that it? Oh no, we got to do an example of this. So here's how vectors can be very useful. This, at its face value, appears to be a very difficult question. There's a bird flying 16 miles an hour in still air. The bird flies due south. So now we have a magnitude and a direction. This is negative 15, 0. Now, there's wind. There's wind blowing, and this is called a vector field or a slope field. And in thermodynamics or heat dynamics and fluid dynamics, a lot of really high-end engineering courses ask themselves, what happens when two things are moving in different directions and they add up? Well, that's what's going on in here. The wind could be, it's blowing east. Oops, sorry, never eat soggy waffles. I screwed this whole thing up. The wind is blowing east, so it's blowing this way at sorry, this should be 16 because it's blowing. It's flying 16 miles an hour in the southward direction, and the wind is blowing 15 miles an hour in the eastward direction. And the cool thing about the way physics works is essentially we're just going to add these vectors up to get you the resultant vector, which is actually the way the crow is going to be flying. That's going to be the direction it goes. So how can we find that out? Pythag. This green vector is negative 16. I'm such an idiot. God dang it. This should be 0, negative 16, the blue vector. It's going right 0 and down or south 16. This one is going right 15. So this one, this green vector, if I didn't have to get this done by tomorrow and I wasn't out tomorrow, I would redo it, but we got to go. This is my first shot and my last shot at this. So that green vector is what we're looking for. Well, hopefully you remember before that green vector is just the result of the sum of these two vectors. So the green vector is 0 plus 15, comma, negative 16 plus 0, which is 15, comma, negative 16. And you might be like, well, that doesn't tell us anything. It's asking us the speed. And you just gave me the direction. Well, the speed is the magnitude. So now how can we find this? Pythag. Negative 16 squared plus 15 squared equals m squared. 16 squared is at 226. I should know that. It's been a long break. 256. Oh, I should have known that because 15 squared is 225. Notice that those become positive, so we're just adding that up and then taking the square root of 481. And now we know that this thing, oh gosh, I'm using Patience's calculator. I don't know how to use it, but thanks for leaving it around. Oh my gosh. Square root of 481. You got that for me, Mikey? And thank you. 21.93 miles per hour. Well, hopefully that makes sense, because it's traveling 16 miles an hour in this direction, and there's no wind in its face. All of the wind is sideways. The wind is sideways here. This is going to be the actual path of that bird, and now the bird is going 21.93 miles per hour, because part of that green wind, or sorry, part of that, oh yeah, that's it. That's how it's, that's it. All right, hope that helps. Boom!